Oh, Mr. Mo, I have a problem. I'm not sure what to do with tomorrow's work. If you help, I will take good notes.
Sally Mae, I'm a math teacher. I should be able to help you with this graphing functions lesson.
Shh. Students haven't heard they need to use graph paper, ruler, and pencils only. They also must show all their work, including showing XY tables. Student graphs must be neat.
Of course, that's why we never use ink to graph in algebra class. Graphing functions.
Oh my, I had no idea these are
Mo's notes. Wow! Well, here's some things you got to know, guys. You got to know what a discrete graph is, and it's they have unconnected points as opposed to continuous graphs that have connected points. Arrowheads are always added to graphs that are continuous unless there is a limit that is applied. We'll talk about more of that whenever we talk domain and range. If a domain is given, the x coordinates are not specifically given. Well, I guess I better back that up just a little bit, but if a domain, the x coordinates, are not specifically given, make the assumption the graph is continuous and connect the points. Don't forget the arrowheads. They need to be drawn at both ends of a smooth line or curve to represent an infinite set of ordered pairs. Also, if a domain is not provided, assume the domain is a set of all real numbers. That brings us to example 1. I want you to graph the function x plus 3y equals 15. In this case, the domain is already provided. The domain is 0, 3, 6, and 9. That means the graph will be discrete. There will be unconnected points. So when you graph, you're just going to leave the points as they are, and you're not going to draw a line. Anytime the graph is not in slope-intercept form, if you look, it's not, because it says x plus 3y equals 15, then you have to solve for y. So this is having solved for y, and I'm making the assumption that you can show the work this way. I know Mr. Miller's charge has shown you how to do this. And then the second thing is to create the chart. So with the chart, you're going to use the values of the domain. You're going to plug those into x, where y equals negative x. Make sure that when you plug those in, that those are in parentheses. So those are all your points. And then the third, you have to graph and plot your coordinates. We move to step 3. Though the result appears to be linear, the graph is discrete, so there is no line that connects each of the points. So you do not connect the dots. The graph is discrete because the domain was specified. Next, we want to graph functions using a domain of all real numbers. So that would get us to example 3. Or is it 2? Yeah, example 3. So the coordinates graphed are connected. When the domain is not provided, assume the solution all real numbers. Then select the 3 easiest values for the domain, which would include, of course, -1, 0, and 1. Even I could do that math, I think. If the graph at this point appears to be nonlinear, then additional inputs need to be added to verify the shape of the graph. Don't forget the arrows. Basically, there are only 3 steps to be able to graph functions. So part 2, or example 2, we want to graph using domain of all real numbers. And if we're given the function y equals x squared, then we'll use friendly numbers first. -1, 0, and 1. Assume the graph is going to be continuous, and there are infinite points because the domain is not provided. Substituting in parentheses will help reduce the careless errors. If you're still not sure what the graph looks like, then go to step 2. You may notice the domain values selected are on both sides of the y-axis. I would caution you in that whatever values you may select for the domain, if the corresponding values of the range don't fit the graph, you can't extend the graph. So the graph looks like this. You notice the arrows are on there, and you had a nice little curve, so this is nonlinear, but it's nonlinear and it's continuous. And example 3, modeling using a function graph. In this example, you determine the domain and determine the range shown in the table. So you have to come up with the table first. You may even have to create the function from the graph, create the table, identify some points for the domain. Since you want to know the spread of the ridge at 4.5 years, draw a vertical line from the x-axis to the graph of the line. Then draw a horizontal line from that point of intersection to the spread of the ridge. So after 4.5 years, if you want to look at the spread of the ridge, it has gone from 0 centimeters all the way up to 11 centimeters. That's pretty significant after 4.5 years. Maybe the state of California is falling off the map. So that gets us to, that's all, folks. Have a great day.